Once we've taken the Laplace transform and combined some terms, we'll often be left with a rational function of polynomials. So this capital F of S here is just this polynomial in S, where we have an order m polynomial in the top and an order n polynomial in the bottom. And so in order to now find the time domain function that corresponds to this complex function, Laplace transform capital F of S, we want to take the inverse Laplace transform. But in order to do that, we want to match it up with elements from the table elements that we've been building. So is it an exponential, is it a sinusoid, and so on. So what we want to do is distill this big rational function into several small ones. And so you've done this before several times for different applications, probably starting back in high school. And the goal here is to rewrite this larger rational function as the sum of several partial fractions. And so that's down at the bottom. And the way that we do that, if we factor the denominator into its terms, s minus pj, then each of these becomes a denominator in each of the partial fractions. So for all of the roots of the denominator polynomial, we'll create a term that will be a partial fraction. And the tricky part, and the part that we have to figure out, is how to find the coefficients C1, C2 to Cn that make this expression, this partial fraction representation, equal to the original function. And so if you, the way that I had learned this initially was simply just to solve a system of equations, but that actually becomes quite cumbersome, and there's a much more efficient way, which is conventionally called the cover-up technique. And so how do we find these coefficients? So the way this works is we multiply the original transfer function by one of the roots of the denominator. So in this case, let's just pick the first one, P1. So if we multiply capital F of S by S minus P1, then that effectively cancels that element out of the denominator. And in our partial fraction representation, we get a quantity that where the coefficient C1 is now without a denominator, and we multiply all the rest of the other terms by S minus P1. And then what we do is we evaluate both left and right hand sides when S is equal to P1. So the left and the right hand sides always have to be equal because F of S should be equal to this partial fraction expansion. And so if it's equal at all values of S, then that means it should also be equal at S is equal to P1. And so the elegant part about this is that it's easy to evaluate the original transfer function multiplied by S minus P1 at S equals P1. And then on the right-hand side, because we're evaluating at S equals P1, all of the other terms are 0. And so all we're left with is C1. And so this seems a little abstract, so it's a little bit easier to see this on an example. So if we consider this example, so now our F of S is capital Y of S, and so it has a numerator polynomial that is factored into S plus 2 and S plus 4, and the denominator polynomial is factored into S plus 1, and S plus 3. So that means we're going to be seeking a partial fraction expansion that has denominators of S plus 1, and S plus 3. And so these are these three terms, and so we need to figure out what C1, C2, and C3 are. And so the way that we do that is we evaluate the function, the Laplace transform, multiplied by, let's pick the first term, the C1 term. So C1 is just going to be, we pick that denominator and we multiply that by the transfer function, or this complex rational function. You'll see that that cancels out the S in the denominator. So all we're left with is S plus 2 times S plus 4 over S plus 1 times S plus 3. So that if a good way of remembering this is if you had left that S in there, when we evaluate this at S equals 0, you'd have a 0 in the denominator, which would be very bad. So the point of this is to cancel out that element of the denominator, so when you evaluate at S equals 0, Now you just plug in s is equal to 0 and you get 2 times 4 in the numerator and 1 times 3 in the denominator. So it's quite easy to evaluate. And so this means that C1 is equal to 8/3. To find C2, we multiply the original function by s plus 1. And so that cancels it out of the denominator. And so now the denominator will just have s and s plus 3. And now we evaluate at that root, which is s is equal to -1. And so if you plug in -1 into each of the terms, in the numerator you get 1 times 3, and the denominator you get -1 times 2. And so that, once you solve that out, that should be, I think I'm missing a minus sign here, that should be -3/2. And then you similarly do that for C3. And so those coefficients get plugged back in to the value of our partial fractions. And one of the things we'll see in class is by doing this, this allows us to take the inverse Laplace transform to find the function of y of t. And we'll talk more in class about how we go from this partial fraction expansion to the time domain function, but essentially we just identify the inverse Laplace transform of each of these pieces. So the inverse Laplace transform of 1 over s is given by the step function. And then the inverse Laplace transform of 1 over s plus a is given by e to the minus at. And so we're using those identities in order to map into y of t.